By now we talked about why we might want to use templates, what happens under the hood when we use them, and today we can finally start talking about how to use them. While there is a lot of intricacies related to templates that often turn the C++ beginners away, I'm going to try to present most of the relevant information in the following couple of lectures. For this one in particular, my ambition is to make it your one-stop shop for all the basics you need to know about writing and using function templates. The class templates I'll leave for the next lecture. So we're starting very gently, and we will dive deeper as we go. That being said, I strongly urge you to go and look at the why and the what lectures before, if you haven't already, because I believe it will make this lecture much easier to digest. Let's start with a very simple function print default integer that just prints a default value of int for now. Running this tiny program will print a 0, just as we expect, but this feels extremely limiting. If we would want to print a default value of more types, we would have to write a lot more of these functions. Function templates provide us with a better way. To declare a function template, we prefix a normal function declaration with the keyword template, followed by a list of template parameters. These template parameters can be used at any place within our function, including its return type, input argument, or the body of the function. Let us begin with just one of such parameters and rewrite our function printDefaultInteger into printDefaultValue function template. Straight away, we notice a couple of changes. Now we have a template parameter t that represents any type, and we print its default value by calling t with curly brackets within a std_cout statement. We call our function template from main, explicitly providing the types int and float for our template parameter at the call site. So the call looks a bit different from how we normally call functions. This is not always the case with function templates, but more on that in a couple of minutes. When the compiler sees our calls, it instantiates the specialization of our function template for the requested types and calls the appropriate specialized functions afterwards. If this is confusing, do look into the previous lecture about what templates do under the hood again. In our simple example here, we specify our template parameter with the word type name. Such template parameters are called type template parameters because they represent, a type. We could have also used the keyword class instead, but I prefer the type name because it indicates that it can stand for any type, while class seems to suggest that it must be, a class or a user-defined type. For whatever reason, though, this is one of those topics in which there are people with very strong opinions on the matter in either way. Please tell me in the comments if you have a very strong opinion on the matter. The name of the template parameter t can be chosen arbitrarily, but a good rule of thumb is to use a name that is representative of what one wants to do with these types, like number or algorithm, or whatever this type should represent. Consequently, we will name them just as any other type in Pascal case. That being said, you will see t used very often, especially in simpler examples, like the ones in this lecture. Speaking of what these template parameters represent, they represent, types that can be used within our function just like any other type. We could create variables of these types or pass them into other function templates, etc. Now, apart from type template parameters, there are more things we can see after the template keyword. Non-type template parameters, template parameters, yes, template word is repeated twice here, variadic templates, and concepts from C++20 on. For now, here we focus only on the non-type template parameters, and we will talk about the rest in the future lectures. Let's illustrate the use of non-type template parameters on another small example function template, printValue, that receives an int template parameter and prints its value. In this example, knumber is a non-type template parameter. Such template parameters are just compile time constants of their respective types, and when we run the code, it will print the values we pass to our template parameters. Before C++20, they could only be integer-like numbers or pointers, but from C++20 on, they can also be floating point numbers or even strings. Please note that the value we provide as our template arguments should be available at compile time. It either has to be a compile time constant or a result of a constant expression, so we cannot use a normal non-const variable when instantiating such a function template. For now, we've looked at using a single template parameter of each kind, but we can have any number of those in any order. We just have to make sure to provide the explicit template arguments in the same order. Furthermore, the template parameters can have default values. We can specify these default values from the end of the template parameter list, although I would not recommend to use default values like these, as they can cause quite some confusion once you forget that you set them somewhere deep in your software architecture. Anyway, as an illustration for some function template do something, we can have a number of template parameters in any arbitrary order and provide the template arguments at the call side in the same order. This is more or less everything we have to know about function templates if they don't have any function parameters. If they do have such parameters that use the template parameters for their types, then the compiler is able to reason about the template's parameters based on the types of these provided function arguments, which is really handy but complicates things a little. We'll start again with a tiny example, with a normal function print that has a single int parameter. Nothing magical about this function. We've seen tons of these by now. However, just as before, we want it to be a function template instead, because we might want it to work for more than just int arguments. We can achieve this by introducing the template keyword before the function, as well as specifying all the necessary template parameters using typename or class keywords. We will also again just print the argument of our function. We can call this function with any type we want, and it will work just as we expect and print the output with the correct types, int and double. What is important to note here is that the compiler is able to figure out the template parameter to be int or double purely depending on the function arguments that we provide, without us providing the types explicitly as opposed to what we did before. That being said, we can explicitly provide the types we want, which makes the following calls equivalent. Now, one small remark here. Think about what happens if you change print double 42.42 to print int 42.42. I encourage you to write what will happen and why in the comments below this video. Now that we are talking about passing arguments to the function, we're still able to do what we learned before and use a constant reference for the input arguments, which prints exactly the same things as before. After we use the const reference with no issues for our template parameter, we might become brave and remember stuff that we discussed when we talked about move semantics. So we might want to use an ref as an input parameter to our function template. However, the naive logic fails us here, as when we use a type template parameter with double ampersand, we are not getting an ref, we're getting a forward-in reference, also sometimes called a universal reference. These behave slightly differently from normal refs and allow us to use a single function to handle both normal references and refs making use of stood-forward function. We will not go deeper into this here, and we'll talk about it separately. We can, however, further extend our printing example in a different way, by adding more template parameters into the mix. Just as before, we just extend the template parameter list to more types. So here we have two template parameters, t1 and t2, that we use to specify the types of our function parameters. And of course, we can run it by either letting the compiler figure out the template parameters on its own or providing them explicitly, which results in printing the expected argument values. Actually, there is one more thing in this example that we haven't seen before. We have 3 function parameters but only 2 template parameters. This is to show that there is no need for a one-to-one correspondence between their number. This totally makes sense too. Just as we can have a function that accepts 3 integers, we can have a function that accepts 3 different arguments of any same type. In our case, we want the first and the last argument of our function to have the same type, albeit first being a const reference, and only the second argument to be of the different type. Now, if we fail to match the types of the first and the last argument by, say, providing a double as the last argument as opposed to the expected int, we will cause a compilation issue that says something about template argument deduction or substitution failing. You might have already started to wonder, if we have multiple function parameters and multiple template parameters that represent the types, can we maybe provide some types explicitly and let the compiler guess the rest? And the answer to your question is yes. Yes, we can. This all gets, again, slightly more complex, but we'll comb through it, no worries. The complications arise because the compiler's ability to guess the types depends partially on the order of the function parameters, as well as on the order of template parameters. One easy way to think about this is this. When we specify the template arguments explicitly, we're specifying them from left to right. Then, when the compiler doesn't see any more explicit template parameters, it looks at the provided function arguments and tries to match them to the function parameters, hopefully figuring out the rest of the template parameters in the process. If the compiler fails to figure out the template parameters, it will throw an error at us. If we try to call our function without the last argument, we will get an error along the lines of candidate expects 4 arguments 3 provided. If we provide a wrong type in the last argument, we will instead get an error about a conflicting type for a parameter, as the compiler will see that our type 3 must be both double and int at the same time to match our template. And feel free to experiment with various error messages here to get a feeling for them. Now I want to switch gears and talk about a very important topic: function overloading. We touched upon it before, but now that we have templates in the mix, we have to look at the whole thing again. Long story short, function overloading allows us to have functions with the same name that differ by their parameters, and to look up the correct one to call based on the arguments provided at the call site. The good news is that if we add a function template into the mix, function overloading still works. To show this, let's replace the first of our functions with a function template. If we run this code, we will see that the call with 42 as input still chooses the normal print function that accepts an int, while the call with 42.42 as input now uses our function template. And the main question that you might be having right about now is, how does a compiler know not to use our function template for 42 too? And that's a great question. The reason it prefers a concrete function implementation rather than a template is that the rules of function overloading will always prefer a non-template function to a template one. Please spend some time experimenting with this. Write various functions, see how the compiler always uses the matching concrete implementation rather than a template. But the overloading story does not end there. We can do so much more with overloading. Just like with any other type, we can treat our template parameter as just some normal types, and largely speaking, if we forget about the template prefix along with its template parameters, then the template functions can be overloaded just as any other function can. Let's see a concrete example where we will overload our function template print for a case when it accepts pointers, and for a case when it accepts a vector of elements. And if we run it, we will get the output that shows that the compiler is able to pick the correct overload when we pass a pointer or a vector into our print function. The intuition behind it is that the compiler will pick that overload which is more specific to the input. So when we pass a vector, it actually fits to 2 of our print functions. However, the vector overload is much more specific. It only accepts vectors, while the basic function accepts vectors and all other sorts of types. So the compiler considers the vector overload to be more specific and picks it. And the same story holds for the pointer. Now try to answer yourself, what if we add our printInt function back into the mix? What will change? Just as we could overload on a pointer type just now, we technically can overload on reference types. The problem is that while a pointer has its own semantics and the compiler is happy to distinguish it from a normal variable, this is not the case for the references. This results in us not being able to have both the version that accepts t and the version that accepts a reference type, say const t ampersand. If we try to compile the above, we're going to get a compilation error along the lines of call being ambiguous. The reason for this is that there is no way for the compiler to figure out at the call site which version we mean. So we can't use both overloads at the same time. However, in most cases we should be good with using constant reference by default. And should we need to squeeze more performance out of our system by copying small types, we will have to go towards partial specialization with classes instead, which we will cover next time. And for those cases when we need to forward ownership of an object through a function, we have a forwarding reference that I mentioned before. Now, one last thing to talk about today is template specialization. Generally speaking, it can be of 2 kinds, full and partial. However, function templates can only be fully specialized, so we will only talk about that kind today. The funny thing is that this kind of specialization basically serves exactly the same purpose as function overloading. And considering that we have this very powerful overloading mechanism for functions that works mostly as we expect it to, the experts in C++ like Herb Sutter and by extension CPP core guidelines suggest that we should not specialize function templates at all. That being said, it is not uncommon to find code that does specialize a function template. To deal with this code, we must still know how specialization looks like and more or less how it is supposed to work. Let us for this go back to the example from before, where we had a function print that was accepting any argument. Now let's say that we want this function to do something different for some random type. For simplicity, let's pick int. We already know that we could overload this function and write a normal function that accepts an int, but we could also specialize our function instead. In order to specialize a function template, we write template and empty angle brackets before the chosen template specialization, and then use the types we wanted to in the first place when writing the rest of our function. Here we provide such a specialization for our print function, and this will do the trick. If we pass 42 as an argument into the print function, the compiler will pick the specialization, while for any other type of argument it will use the base function template. So if all seems to be working, then what's the issue? Why is it that it is suggested not to specialize function templates? And this topic is quite confusing because of the complicated rules of template argument deduction. The best thing I can do is give a couple of examples that look a little counterintuitive to me and to many other people for that matter too. Let us start with an example related to passing objects by const references. Assuming we have some relatively large object, we would have the code that does something with it using a function template process. Now we want some special processing for our object, so we have a bright idea to specialize the function template process, and we use a const object reference as an input type because we don't want to copy our object. Intuitively looking at the code, one could expect that a specialization that fits perfectly to accept our const object reference would be called, but unfortunately if we run this code, we get the following output. This indicates to us that the specialization was not called, and the object was copied because the process base function template was called instead. The reasons for this are slightly involved, but the idea is this. Template argument deduction never deduces a reference type, so t cannot be a reference type. In our case, it deduces t to be object, which means that there is a function instantiated from our template void process object and takes an object, which is the exact match to the object that is being passed. This instantiation is better than our handwritten specialization that takes a reference type instead, so the compiler never picks our specialization, at least that's my understanding for now. We can fix it in a hacky way by explicitly forcing the compiler to pick the right specialization by changing the call to our function. With this modification, the correct specialization is called and the object is not copied. But it is quite hacky, and still the actual better solution would be to overload the function instead of specializing it. If we run this example, we get the expected output. So the object is not copied and our overload is preferred to the general function template. Another classical example is the so-called Dimov-Abrahams example. It involves both a function template overload and a function template specialization and has confused a lot of people in its time. We have a function template process and its specialization for int star or int pointer parameter. We then create an int star variable and pass it as a parameter to a function process. The compiler sees that there is a template, sees a specialization too, and correctly picks it, so we're good for now. The confusing parts begin if we now add an overload for any pointer type after the specialization, and it is important that we do it after. If we run this code, the overload is going to be called, not the specialization. And this is confusing because our specialization is still the exact match to the type we pass. So if it happens that we have an overload after we define the perfect specialization that fits to our passed argument exactly, suddenly this overload will be picked. Now, the key to understanding this behavior is really well described by Herb Sutter in his post, Why Not Specialize Function Templates. The specializations do not participate in overload resolution, which means that first an overload is picked, and only then a specialization of that selected overload is picked, if any. So in our case, the process t star is a better overload, so it is selected. The process int star specialization is not selected, as it is a specialization of process t and not process t star. Anyway, just making it an overload fixes the issue for good. By the way, if you made this far, I have a question for you. What will happen if we move the specialization below the overload in the original example? Write your answers in the comments to the video, including the reasoning for what is happening, and let's chat about it there. Okay, one final thing for today is that everything related to templates happens at compile time, which has its consequences. One of the errors that I see beginners do, and did myself many years ago, is to assume that the compiler cares about the logic inside the function which it compiles. The reason goes along the way that if we logically guarantee that the code pass will never be taken, then it's okay for this code pass to not compile, and the compiler should still be fine with this. And unfortunately, or fortunately, this is not the case. Let's illustrate this with an example. Let's say we have a function getLengths that should return lengths of various objects, and it has a couple of template parameters, the non-type enum value representing which type we expect, and then the type template parameter that actually represents the type of the function parameter. We then try to write the code that logically seems quite sane. We have an if statement in our function, and we pass the type kString enum value whenever we use our getLengths function with a string, and the type kNumber value when we use it with a number. It might be reasonable to assume that this code should compile, but it does not, with an error that complains on our number not having the size method. The reason for this is actually quite simple. The compiler does not care about the logic in our function, as the logic is runtime logic. It cannot assume that just because we did not happen to call all the possible paths through our function, nobody else would. In the end, if this function gets compiled into a library and distributed, somebody might call it in a different way. So it has to compile as a whole. And of course it doesn't, because many types don't have the size method. I've seen this mistake being made countless times, so I wanted to explicitly mention it here. I also have a piece of good news related to this. We now live in the world of modern C++, that is at least C++ 17, and we have more tools at our disposal to achieve what we want in this situation. What we could do now is to use the if constexpr, a compile time cousin of the normal runtime if, which will allow the compiler to actually conditionally compile parts of our function based on the provided parameters. With this change, the code compiles and runs as expected. And if we're feeling adventurous, we could even say that with this example we dipped our feet into compile time metaprogramming. In reality, we don't really need an explicit enum for purposes similar to the one in the example, and we have more tools for conditional compilation as well as tools for estimating traits about our types, but more on that in the future. If you've made it this far, you're a hero. You're clearly interested in templates and determined enough to listen to me ramble about them for a long time. So why not subscribe to this channel to not miss what's coming next? I know this seems like it's a lot of information at once, but trust me, it becomes easier with time. Also, we covered not only the basics of using function templates, but also what not to do, and as well as why we shouldn't do it, which doesn't help making this lecture easy to digest, but will make your life easier going forward. Anyway, as a very short summary, today we've covered most of the important parts of function templates. We know how to define them, what template parameters they can accept, and how to call these function templates. Furthermore, we now know that we can and should overload function templates, but we probably should steer away from specializing them. And honestly, with this information at our disposal, we can go a pretty long way in the world of generic programming. The next lecture is going to still focus on how to use templates, but now for classes, where there are slightly more details and where specialization actually does play a much more important role than with functions. But if this lecture is firmly placed within our heads, we should have little issues figuring out class templates too. And if you feel that you still need a refresher on what is it that templates do under the hood, then click on the video right over here. And at this, as always, thanks a lot for your attention. Please do not hesitate to write any comment and chat with me in the comments under this video, and I'll see you in the next one. Bye!